Past ice ages helping to predict future extreme weather patterns. Discover how ancient climate data reveals insights into future El Niño patterns and their global impacts in a warming world. El Niño events, periodic warming of sea surface temperatures in the Pacific, are among the most influential drivers of global climate variability. These phenomena, occurring every 2 to 7 years, disrupt weather patterns worldwide, causing droughts, floods, and wildfires. Predicting how El Niño might respond to human-induced climate change is a priority for climate science. However, the challenge lies in reconciling conflicting model predictions and historical uncertainties. Recent research, led by Kaustubh Thirumalai from the University of Arizona, offers new insights by combining advanced climate models with ancient climate data. This study, published in Nature, examines the mechanisms behind El Niño changes during past and future climate states, focusing on the last glacial maximum, about 20,000 years ago, to better understand future variability. The last glacial maximum, a period marked by extensive ice coverage and dramatic climate shifts, provides a unique window into Earth's climatic past. During this era, ice sheets blanketed much of North America and Europe, reshaping oceans and ecosystems. Understanding how El Niño behaved in this dramatically different climate could reveal how it may evolve under anthropogenic warming. Using the Community Earth System Model, CESM, a sophisticated tool designed to simulate Earth's climate, researchers reconstructed conditions from the last glacial maximum to the present. This model, developed by the National Center for Atmospheric Research, incorporates contributions from institutions worldwide and has been validated against extensive climate data. The team's approach included analyzing microscopic marine organisms called foraminifera. These creatures, floating in the upper ocean, build shells that capture the temperature of their environment. After their brief lifespan, their shells sink to the seafloor, becoming part of sediment layers. By studying these layers, scientists reconstructed ancient ocean temperatures. These beautiful, microscopic creatures lock in ocean temperatures when they were alive, creating a snapshot of past climates, explained Thirumalai. By examining individual shells from the same sediment layer, the team captured seasonal temperature variations, allowing for a detailed comparison of El Niño variability between glacial and modern conditions. The study revealed that El Niño variability was significantly lower during the last glacial maximum than today. This reduced variability was linked to a deeper ocean mixed layer and a stronger Walker circulation, which weakened the coupled ocean-atmosphere interactions essential for El Niño formation. Under greenhouse warming, however, these dynamics shift dramatically. The simulations predict a shallower mixed layer and a weaker Walker circulation, conditions conducive to more frequent extreme El Niño events. Such events, characterized by the rapid eastward expansion of warm waters in the western Pacific, amplify global weather disruptions. El Niño is a formidable force of nature, said Thirumalai. It disrupts ecosystems, agriculture, and infrastructure worldwide. These findings align with paleoclimate records from the tropical Pacific, which show reduced temperature variability during glacial periods. By validating the model's ability to simulate past conditions accurately, the researchers strengthened its credibility for predicting future El Niño behavior. The mechanism identified by the study hinges on ocean-atmosphere feedbacks. During El Niño events, warm waters from the western Pacific expand eastward, disrupting normal weather patterns. Greenhouse warming intensifies these feedbacks, potentially making El Niño events more extreme and frequent. This insight bridges gaps in our understanding, connecting past climatic behavior with future projections. As greenhouse gas concentrations rise, the study predicts a pronounced increase in El Niño variability. This trend suggests that extreme El Niño events, similar to those in 1982, 1997, and 2015, could become more common. These events have historically caused widespread coral bleaching, tropical forest fires, and heat waves, among other disruptions. The mechanisms driving these changes are rooted in feedback processes within the ocean-atmosphere system. El Niño's evolution depends on interactions between sea surface temperatures, ocean currents, and atmospheric winds. Greenhouse warming intensifies these interactions, leading to greater variability. The societal implications of more frequent extreme El Niño events are vast. Agricultural yields could suffer from prolonged droughts in some regions while others face catastrophic flooding. Infrastructure, public health, and ecosystems would all experience increased strain. Understanding these patterns is crucial for developing mitigation and adaptation strategies. If the model can accurately simulate past climate changes, it's more likely to give reliable predictions about future changes, Thirumalai noted. This confidence in model projections can guide policy decisions, helping societies prepare for a more variable climate future. This research represents a significant step in understanding the dynamics of El Niño across climatic states. By linking past and future mechanisms, scientists can refine predictions and guide preparations for the societal impacts of extreme events. These findings underscore the importance of integrating paleoclimate data with advanced modeling to address uncertainties in climate projections. Future efforts will focus on refining these models and exploring additional data sources, ensuring a comprehensive understanding of El Niño's role in a warming world. Collaboration among international researchers and institutions will be critical in this endeavor. Improved data collection methods, such as enhanced sediment core analysis and satellite observations, could offer even more precise insights. As climate science advances, the lessons of the past will continue to illuminate the path forward, helping societies adapt to an uncertain future. The ability to predict El Niño's response to climate change is not just a scientific pursuit but a necessity for safeguarding global well-being. By understanding the complex interplay of factors driving these events, we move closer to ensuring resilience in the face of climate variability. The research led by Kaustubh Thirumalai and his team at the University of Arizona has opened a new chapter in climate science by investigating how ancient El Niño patterns, preserved in marine sediments from the Last Glacial Maximum, can provide insights into how the phenomenon may respond to future global warming. This study, published in Nature, combines advanced climate models and paleoceanographic data to offer valuable predictions for future climate scenarios. The ancient climate data used for this study is based on the study of foraminifera, microscopic marine organisms that create shells in response to their environment. These shells act as time capsules, preserving temperature information over thousands of years. By studying the changes in ocean temperatures locked within these shells, scientists can reconstruct climate patterns from the past, such as the nature and variability of El Niño events during periods when the Earth's climate was vastly different from today. The focus on the Last Glacial Maximum, LGM, approximately 20,000 years ago, is particularly important. During this period, the Earth was much cooler, with ice sheets covering large parts of the northern hemisphere. These conditions fundamentally altered ocean circulation patterns and atmospheric interactions, which in turn affected the behavior of El Niño. By analyzing how El Niño manifested during this cold period, scientists can better understand how it might evolve under the current trend of anthropogenic climate change, where increasing greenhouse gas emissions are driving global warming. One of the significant findings of this study is that El Niño variability was much lower during the LGM compared to modern times. This reduced variability was linked to a deeper ocean mixed layer and a stronger Walker circulation, a key atmospheric pattern that typically helps to moderate El Niño conditions. The result was a more stable Pacific Ocean climate, which contrasts sharply with the highly variable conditions we experience today. However, as the Earth warms due to climate change, simulations predict that these natural systems will undergo dramatic shifts. The model forecasts a shallower mixed layer in the ocean and a weaker Walker circulation, both of which facilitate the development of more extreme El Niño events. Under these conditions, El Niño could become a more frequent phenomenon, amplifying global weather disruptions such as floods, droughts, wildfires, and heat waves, which can severely affect ecosystems, agriculture, and human livelihoods. This research is of particular importance as it connects past climate events to future projections, helping to bridge the gap between paleoclimate data and modern-day climate modeling. By comparing the reconstructed climate of the past to future scenarios, the study provides a more accurate picture of what we can expect in terms of El Niño behavior in a warming world. The implications of these findings are significant. More extreme El Niño events are likely to cause widespread disruptions to weather patterns, leading to catastrophic flooding in some regions, droughts in others, and exacerbated heat waves. These events could strain agricultural systems, leading to crop failures and food shortages. Coastal and low-lying areas may be especially vulnerable to flooding, while regions prone to drought may face longer, more severe dry periods. Furthermore, extreme El Niño events have been linked to large-scale coral bleaching, which threatens marine ecosystems and biodiversity. The feedback mechanisms driving these changes are central to understanding how El Niño could evolve. As warm waters from the western Pacific expand eastward during El Niño events, the interaction between ocean currents, sea surface temperatures, and atmospheric winds becomes increasingly intense. Under greenhouse warming, these feedback loops become amplified, leading to even greater fluctuations in temperature and more extreme weather events. These changes challenge existing models and force scientists to refine their predictions in light of new data. The societal consequences of more frequent extreme El Niño events are far-reaching. Not only could agriculture suffer from unpredictable rainfall patterns and droughts, but the destruction of infrastructure, the spread of diseases, and the loss of biodiversity could further strain human societies. Coastal communities may also face rising sea levels and increased storm surges, leading to the displacement of populations and long-term economic damage. This research underscores the urgent need for proactive measures to mitigate and adapt to these changing conditions. By improving our understanding of the mechanisms behind El Niño, policymakers can better prepare for its impacts. This includes strengthening disaster preparedness plans, investing in resilient infrastructure, and adopting agricultural strategies that can withstand extreme weather patterns. Governments, international agencies, and scientists must collaborate to develop strategies that address both the immediate and long-term effects of climate change. Moreover, the study's findings emphasize the need for continued research into the dynamics of El Niño and other climate patterns. Paleoclimate data, such as the one used in this study, is invaluable for refining climate models and improving future projections. As climate science evolves, so too must our understanding of how past events shape our future climate. Conclusion: as global temperatures continue to rise, understanding how phenomena like El Niño will evolve is critical for predicting and preparing for extreme weather events. The combination of ancient marine data and advanced climate modeling provides essential insights into how El Niño might intensify in a warmer world. The study's findings highlight the increased potential for more frequent and extreme El Niño events, which will disrupt ecosystems, agriculture, and infrastructure globally. Moving forward, the integration of paleoclimate data, advanced climate models, and global collaboration will be key to mitigating these impacts. By learning from the past and preparing for the future, we can better equip societies to adapt to the challenges posed by climate change and ensure a more resilient future for all.